welcome again, everyone online, everyone who's here to the Cambridge RSE seminars. As I regularly tell my colleagues and friends around Cambridge, your number will eventually come up to present here. And unfortunately, today is me, but fortunately also you have Joe, who's going to be talking to us about some of the work or software that we've sort of developed whilst working at Cambridge, and is now used slightly more widely as an open source tool. So I guess I can get started. So the topic is FTorch, which is the name of the software, and specifically what we're doing is looking at facilitating hybrid modeling in scientific computing. By hybrid modeling, what we mean here is a combination of compiled or numerical models running on high-performance systems with some element of machine-learned code or machine-learned components. So the slides are available online if you want to go and find them and follow along, and there's some other licensing bits and pieces there. So as I say, the motivation for this is coming from more of the numerical end. So where we work, the Institute of Computing and Climate Science deals predominantly with kind of large weather and climate models. But when I talk about these models, you can also think your large-scale plasma simulations, think cosmology codes, think materials, quantum chemistry, any kind of large compiled code running on multiple nodes, lots of compute. And so thinking about weather and climate models, typically sort of these are made up of many individual sort of submodels or subcomponents. Here we have kind of a core which will look after the fluids equations of the atmosphere or the ocean, but then there's various other components of those models, for example, the precipitation or radiation, contributions from the cryosphere, that are made up of sort of separate submodels that run and feed into and out of this kind of fluid dynamical core. And often these are running at sort of very small scales, or modeling processes that occur at very small scales, because when we divide things up into a grid box, typically all we can model are phenomena that occurs on the scale of the grid box. So in the atmosphere, if we're talking about 60 or 100 kilometer grid boxes, we can't capture processes such as individual clouds. So you can imagine you could have water content, but that could be a sea fog, it could be very high cirrus clouds, it could be cumulus deep convection, all of which give rise to sort of very different processes. And so we need a way of kind of modeling at the what we call the subgrid scale. And this is true of, as I say, other simulations. So fluids have sort of turbulence, plasmas again turbulence, and sort of even smaller scales than that, we've got physical phenomena that we're trying to capture. And so the way we do this is usually with something that's called parameterization or subgridded models. And this is where we construct some kind of set of equations that we feel represent those processes that we can't model at the appropriate scale, so that they do have the correct effects or the knock-on effects within the simulations. But doing this, there will always be assumptions, there will always be approximations. And so these do often end up being a very large source of uncertainty within our models. So this is where sort of machine learning has come in and provides sort of a new route to looking at these sorts of phenomena. So traditionally, sort of machine learning, we think of it much more as an end-to-end process, sort of a black box. We feed in some input and we get some output out of the other end that we can say something about. This is not true in the applications that we're looking at. What we're particularly interested in is just replacing sort of a single component of the models that we're dealing with. So we want to sort of retain the numerics, retain the scientific explainability for everything that is working well. But if there's something where we feel we can learn from real world data, or perhaps we can conduct high-resolution simulations and then learn a subgrid model from those high-resolution simulations that do capture the behavior, then we want to construct that and just replace that single sort of point of weakness or point of uncertainty within our model. However, doing so, there are various challenges. So sort of reproducibility, there's the question of when we train this separately on some other sets of data, how do we know that it's going to function correctly in place as part of a much larger model? There's also questions around reusability. So if we want to make these available to many other models, How do we avoid sort of getting locked on particular model resolutions or resolutions of training data? And how can we sort of make these easy to retrain or adapt for users? And then finally, sort of the question that we're particularly looking at today is the question of language interoperation. So what I mean by this is that typically your machine learning frameworks will be in Python, sort of either PyTorch or TensorFlow. Pick your favorite one and explain why it's PyTorch. But the models that we're dealing with, particularly in the weather and climate domain, but this is also true for many other areas of scientific computing, are written in Fortran. Some domains I know are favoring C++ now, but particularly weather and climate, there's a strong bias still towards using Fortran models that have been in development for a long time, but also utilizing sort of the array native syntax there. And so the question is, when you conduct your machine learning in Python, how do you effectively get it into those Fortran models? And that is the question which sort of FTorch provides a solution for. So before we think about FTorch, there's a few different approaches. There's the sort of the pure Fortran approach, which is favored by some. I think Fortran is gradually moving away from this mindset. The most basic of which, and what we see a lot of researchers we work with doing, is to take a net that they've written and they've trained within PyTorch and then re-implement it within Fortran. At the end of the day, sort of feed-forward nets or CNNs are just matrix multiplication. And I said a second ago that Fortran is great for arrays and matrix multiplication. But there's also downsides to this. So it's providing additional work to kind of rewrite code that you've already been using. There's also reproducibility issues. We'll come on to later, but sort of column major to row major. How do you make sure that you've really not cocked that up? And then there's also the question of, sort of like I said, CNNs or feed-forward ANNs are very, very simple to implement. But now machine learning, particularly in these kind of hybrid modeling cases, is moving to more and more complex architectures, which are not straightforward to re-implement within Fortran, particularly not to the level that, say, PyTorch or others have done so. The other option is there are now emerging some pure Fortran machine learning frameworks, sort of two leading ones listed here. However, these are often academic-driven projects, and they always lag behind sort of the latest improvements by the more industrial companies, say, behind PyTorch. So on the other side, there's kind of doing the language interoperation, saying, if we've got something in Python, how do we then use it without doing, without having to redo all of it within Fortran? So one option is ForPy, which is just a very nice Fortran module. You drop it into your code, add it to your compilation, and it will provide you the ability to exchange data types into and out of Fortran to a Python runtime. It's really easy to add, and if you just want to get data in and out, it's actually quite a nice solution. But the challenge comes when you want to use it with sort of a PyTorch, using tensors and more elaborate data types. And it's also not had an update, I think, in 5 or 6 years now. SmartSim is another solution. So here you continue to keep your Python and your Fortran separate, but you write a sort of orchestration script in Python that can speak to both of those two elements. And then you're able to exchange sort of the data over a Redis API, running both codes sort of in tandem when you need it. So you write out your data from Fortran, it's read in by the Python, that writes something back out, and it comes back across. So this is very, very versatile. You can sort of do any Fortran you want, any Python you want, but there is quite a steep learning curve, kind of writing this orchestration layer above your existing codes, and it does involve data copying, which can get quite expensive. And then we've got the Fortran Keras bridge. So this was perhaps the original player in this space, was specifically looking at dealing with Keras, which is now TensorFlow. But again, there's been no updates to this in about 5 years, and the scientific community in particular has moved towards using PyTorch for scientific model development. And then also there's TorchFort, which takes a very, very similar approach to FTorch, and was started, I think, about a year afterwards by NVIDIA. But it's particularly focused on deployment on NVIDIA hardwares. So there are a few solutions out there. So when we came to develop the code that we've got, we had focus on efficiency, but I want to be clear here, particularly from the RSE perspective, that there's kind of two types of efficiency. So there's the traditional kind of computational efficiency that we're concerned with. This is, are we doing things with the minimal amount of compute, the minimal amount of data transfer, sort of the minimal amount of core hours, which we all want. But also when we're running scientific models, it's not like we're running them continuously in deployment. Often sort of we do a lot of development, we do a lot of experimentation to get one particular result. And so working with researchers, we also had a focus on the developer side of the efficiency. So we wanted to make something that was also very, very easy for someone to be able to pick up and use in their own code, sort of very, very familiar, abstract away as much as we could sort of the technical difficulties, so that a PhD student, when they start their PhD and their supervisor says, oh, you're going to train a Python model and then you're going to put it into my Fortran code, they can actually give that a punt and work through that rather than having to sort of cry painfully about data transfer and end up doing a computer science and HPC degree instead of what they originally thought they'd be doing. So yeah, as I say, from the scientific or the research side, I think both of these have important consideration, which might not be true elsewhere. So that brings us on to FTorch, which is the software we have to solve this. So how do we do it? So PyTorch, I said, was a Python framework, but if it was pure Python, we wouldn't have the efficiency that we get for training these models. So really, when you use PyTorch, what you're actually doing is using a Python interface to an underlying C++ framework for training machine learning models. And it's the nice folks at PyTorch have given us an API interface into this C++ layer, so we can access that directly rather than using Python. So then the other half of this puzzle is that using C or C++ code from Fortran is relatively straightforward, caveat there, using the ISOC binding module, which allows you to sort of wrap around C or C++ libraries and call those functions from within, directly from within Fortran itself. So what we'll do is when users have developed some code in PyTorch, trained a model in PyTorch and think they're ready to go for implementation, we then get them to save this out into a portable format that's called TorchScript. And then this is a form that can be read and run directly by the C++ API. And then our side of this deal is that we then provide a Fortran API that wraps around the C++ API with a little bit of sort of sprinkling of Fortran kindness for the users, but really it kind of wraps and abstracts away the more complicated details to use to leave kind of quite a familiar interface for those who are then writing Fortran, who've trained and used their models within PyTorch. And we'll have some examples of that in a moment. So to summarize sort of the approach, traditionally what you might have done, say, with 4Py or with something like SmartSim, is you would take your Fortran code, you would call out to a Python runtime, that Python runtime would run PyTorch and then send things back. And to do this, you also need a Python environment. If you're running on a HPC system, there's reasons you might not be keen for this. Insert obligatory XKCD cartoon here. And so what we will do instead is go directly from the Fortran to the underlying PyTorch by way of sort of a C++ bridge. And at that point, I think I'm passing over to Joe.
Thank you. Good. So yeah, I get to come in and talk about highlights, which is nice. So this is going to be some of the highlights of FTorch from the developer point of things. So it's easy to clone, build, and install, and supports a couple of different building approaches. One of which is with CMake, and this is supported on Linux, macOS, and Windows, and we're regularly testing all three of those. Easy to link, again, using CMake, or you can just use GNUMake, and this sort of linker flags that can be shown there. We've been investigating other packaging solutions as well recently, and hopefully there'll be something that we can report back on that sometime soon. FTorch provides some user tools. So one of them is a PT to TS script, so PyTorch to Torch script. So if you want to use your PyTorch model that's been written out into a file which has this .pt extension, you need to convert it into this Torch script, which is a sort of more portable format that can then be read from C++ backend. So that's kind of a bit of a side note, I suppose, but this is a key utility that we provide to allow users to do that. We've got quite an extensive example suite now that covers everything from just playing around with tensors and sort of simple nets, which is like a very naive example, through to more the kind of neural networks that you would see in practice, and then onto sort of advanced features like using multiple GPUs, NPI, and doing automatic differentiation. And we've got full API documentation and a lot of user guide pages on the website as well that go along with that. And we kind of know that these are sufficiently good because I'm going to talk a bit later about some of the case studies of people that have used FTorch. And in a lot of cases, we didn't even know that they were using it until like we read the paper or we saw their talk at a conference. So when we actually chatted to them, we found out that most of them just read the documentation, and that was enough to get them going. So we're pretty happy with that, and we make sure that it stays up to date. FTorch is free and open source. It's licensed under MIT, which is very permissive, and it's actively getting contribution from users both in our team and then recently we've got a lot more contributors from outside of our team, which has been really nice. Following talks like this that we've given, people got interested, hackathons, and then also just random people that just found it on the internet. I'm also going to talk about some highlights from the computation side of things. So we are using the implementations from PyTorch directly. So it means that the features and the future support, it sort of just come through naturally. We handle any updates to API that might happen, although we're grateful that it doesn't happen too often. But so long as you update your PyTorch, you can make use of any new features that come along, which is really nice. And you also get reproducibility through that. We provide a few different backends for offloading to GPUs. So CUDA is the one we've supported for the longest, but in the last year or so, we've added support for HIP or AMD. NPS, which I think there's two different GPU-related things called NPS. This one is the one that is the kind of GPU you'd find in a MacBook. So if you want to run FTorch on your MacBook's GPU, then you can do that. And the XPU is Intel. We also handle the issue that you may have thought about, which is going between Python or C and C++ and Fortran. You've got row major versus column major issues. So if you try and do that conversion yourself, you can get some real headaches. And we take on the headaches for you. So we've had a lot of those, and we're pretty happy with how it's all set up now. So you can happily just move your tensors between the two programming languages without worrying about that. There's also a no copy access in memory on the CPU. So I'll show you what I mean in a diagram. So suppose you've got some Fortran arrays. So there's this like X and Y thing that you see on the left there. And you want to do some computation using a neural network and then get out some other arrays, A and B. So the way that FTorch works is it has pointers that associate directly the Fortran arrays to the Torch data types. So when you once you've set everything up, when you do that computation that calls the inference in PyTorch, it will be working with the same data that you were setting up in Fortran. So there's no data transfer going on here. It's just working on exactly the same memory, which is very neat. Some of the other solutions that Jack mentioned earlier aren't able to do this. They have to do data transfers, which can become a bit of a bottleneck. It says on CPU, so that's an important note. As soon as you go into the GPU, you can't do this anymore. I think potentially if there's a unified memory space between two, you could make it work, but we still need to investigate that. We've not tried that out. So a bit of code. This is a script that shows how to save out a model from Python. I thought it was going to go through the different bits. basically you can see that it's this torch code, and we create a tensor, and then we load a model, and we create a tensor. The tensor is only actually required in one of these cases. But basically, when you're writing out to torch script, so this is kind of like a mini version of the PT to TS script that I mentioned. There's two options. You can either do scripting or you can do tracing. And I won't go into the details of exactly what that means, but it's two different ways that you can convert this PyTorch model into this portable torch script format. And they have different advantages and disadvantages. But in either case, you can do this with FTorch, and then you can have this PyTorch model ready to be used in Fortran. It also includes the weights and the biases in there with it. So you can train your model in Python and then deploy it in Fortran. And then this snippet of code here shows what you would do using FTorch's syntax in Fortran. So the most important thing is to use FTorch, so that imports the functionality. We set up some tensors. So you can see that these are actually arrays of tensors, but that's kind of a minor point. There's this torch tensor derived type, which is like a class in Fortran. And basically, we create these. We initialize some input data where here in data is an array. And then we can use this torch tensor from array to associate them together. So this is what I was saying before about how we're having the tensor just points to the Fortran, the data that's contained in the Fortran array. So here we're kind of associating them together, and we're saying that the tensors live on the CPU in this case. And then once you've done that, you can load a model also on the CPU, and then call torch model forward. So what this will do is it will run inference on the input tensors, and it will update the output tensors. And because the output tensor has been updated, the Fortran output array has also been updated. And you can do whatever you want to do with that in the next line, on line 90, the next one. This has been a hot topic in our group recently with torch delete. So we were always recommending that you should clean up your tensors, but we've managed to set up finalizers sufficiently well, and we're now very confident there's no memory leaks, thanks to some help from Nikolai. So you can quite confidently now just not call torch delete if you don't want to. This will all happen automatically at the end of the subroutine or program. But you can do it if you really want. Well, there might be some reasons that you want to do that. To go on the GPU, it's not too much more work. So as I said before, we specified in the torch tensor from array that you have the CPU device. In this case, we're using a CUDA device. So both the input tensor and the output tensor are on it. They're very similar characters. The input tensor here is on a CUDA device. The output tensor is on CPU. And the model is also on the GPU. So basically, you'll do your inference on the GPU, and then that will automatically be transferred into an output array that's on the CPU ready for you to use for some downstream code. There's also this device index there. Yeah. There's this device index that you see at the end, which defaults to 0 if you've got a GPU. Basically, this allows you to have multiple GPUs that you're sort of sending data to at the same time. So you can send some tensors to different GPUs. And we sort of leave that all to be managed by the user. So again, you've got a device index 0 in this one as well. There's an example in the FTorch examples, which shows you how to do this with multiple different GPUs. I've already mentioned that we support these different devices. Last year, we published a JOS paper, so the Journal of Open Source Software. So it's quite a short paper that sort of encapsulates FTorch version 1.0. And we recommend that you take a look at it if you're interested in FTorch. It gives a bit of a snapshot of what it's all about and what it's been used for up until that point. We've also got the training materials that I mentioned in the FTorch repository, so examples and things like that, and documentation. But we've also got a workshop that we regularly run, usually in person. I don't know if we've ever done an online one, have we? I don't think so. So yes, it's hybrid, so you could do it online. And you could even just follow it at your own pace as well. But typically we run this as an in-person event at conferences or summer schools or things like that. I'll talk a bit about applications and case studies. So these are all examples of people using FTorch for their projects. You want to go back to you?
Yeah.
Yeah.
Thank you. Yeah, so the first project that kind of we worked on a little bit, and I think Simon is on the call somewhere, was with a sort of simple atmospheric model where it was mostly a proof of concept. So the researchers had trained a neural net and they were then trying to deploy it with 4Py, which I mentioned previously. And they'd got the code to work and the results looked correct, but the problem was it was taking much longer than just running sort of the model they were trying to emulate. And this had become a problem with the publication process and also practically kind of the operational side. No one's going to run it if it takes 10 times as long. So this was when they approached us to sort of see if we could find a better solution to this. And it was the implementation here, which was sort of originally coded into this model, that was eventually we realized it was going to be useful enough to other people across the domain, and it turns out beyond the domain, that we sort of pulled it out and made it into its own standalone library. So this was, like I say, sort of originally was quite proof of concept, but this work continued to actually do some quite interesting work where, having coupled one neural network, they then showed that if they train a series of neural networks, all with identical architecture, or with identical training data, or with identical training loops, and all they change is the random seeds on the computer before they conduct that training process, they show that when you couple it back up, actually you could end up in very different regimes of behavior within your atmospheric model. And so it's not enough to sufficiently say we've got an R squared of 0.8, this is going to be great. Actually, there's a lot of feedback when you couple that up to a sort of part of a larger system. So that's quite interesting. Moving on from that, there's work that's been done with ICON. So this is the weather model that's used at the German weather system, or German Weather Forecasting Center. So this, I think, as Joe mentioned, it was quite nice because it was something that I was presenting at a conference, and then the talk after me was Julian presenting this. And until that point, we'd had no idea that anyone was doing anything with this outside of our direct collaborators. So it's quite a nice sort of indication that the documentation, the examples are working. And actually, sort of beyond those original studies, they've now gone on to build sort of multiple machine learning components into one model. And they've been looking at doing this rather than kind of a specific coupling. They're actually developing a FTorch interface that goes into their model. And they're particularly focused on running on sort of GPU systems as well. So appreciate the easy offloading that Joe was talking about a second ago. A similar story is CESM. So this is the Community Earth System model. And this is sort of a leading climate model, part of the Model into Comparison project that sort of feeds climate reports. So here we did some work to integrate FTorch into the build system for this model so that it could be used by users sort of throughout the code. One of the earliest applications of that was Will, who helped us with the integration. So he did some interesting work looking at sort of overall model biases. So rather than focusing on one small specific component, like I mentioned in the motivation, what he did instead was say, we know that there are inherent biases to models. So if we sort of take the outputs, compare them to some real world observations, so here weather data, and sort of learn what those biases are based on the current state of the model, can we then implement some kind of machine learned bias correction at the end to improve the accuracy? So think of it sort of a bit like learning how data assimilation works, but then being able to apply data assimilation without the data. More recently, we've sort of been told that similar to the ICON project, CESM are looking to use FTorch kind of as an interface for multiple components in their ML enhanced version of CESM. And we're hoping that we might do some work with them sort of to make sure this is done as efficiently and smoothly as possible. So keep an eye out for that. And then the last one I've got is some turbulent plasmas. So often when I'm presenting this as part of ICCS, we focus on kind of the climate applications, but given this is a wider audience, this is some work by UKAEA, who came to a workshop, sort of a broader workshop on hybrid modeling that Joe and I organized at the end of last year. And here they've been using FTorch again, sort of to embed learn surrogate models within a larger code base. This one is for turbulent parameters in plasma, fusion simulations with plasma. So again, the smallest scales can't be accurately captured by larger models, or if they run very, very high fidelity models to capture this behavior, it uses up a lot of compute and it limits sort of what they can do with the available resource. So they used Gaussian processes. So actually using a library that builds on top of PyTorch, GPyTorch, giving you access to Gaussian processes. But it turns out that everything that's done in GPyTorch can be saved as torque script and could then be embedded within their Fortran models. And this, we are told, is sort of took them from simulations that were running sort of over the course of 2 weeks down to 4 hours on a 60-core machine. So quite a nice result to hear about. And again, someone who turned up to our workshop and talked to us about this without us sort of being hugely aware that they were doing it in advance. And then I used to have a list here of other people who were doing things. This has actually grown too long to fit on a slide, which is quite nice, but we've got a full list of sort of community projects or papers that we're aware of. So if there's anyone who's using this that's not on there, please do get in touch and let us know. At which point I'll pass back over again to Joe, who's talking about sort of some of the newer advancements or work in progress that we've got, because this is not the end.
Thank you. I will just make a note actually on this slide. So there's all these other things that other people are doing, but there's actually something that we're just kicking off as well. We're hoping to do an inter-comparison study with some of the other solutions that Jack mentioned earlier on. So there's several different packages that do a similar job or solve the same problem in a different way. So we've recently got in contact with the people that develop those packages, and we're hoping to do something in that direction as well, which would be quite a nice case study, I think. But yeah, I'll talk about AutoGrad, which is PyTorch's automatic differentiation backend, which we exposed in FTorch last year, and how this can be used to do online training. If any of that's unclear, hopefully it will become clear. So up until recently, FTorch has been used by researchers who wanted to run their models that have been trained offline. And what that means is that they basically have some training data that they'd saved out from a simulation that was sort of encoding what they're expecting to get from their machine learning implementation. And then they would do the training in PyTorch using Python scripts in what's kind of like the usual sense that people do that. And then having trained their model, they would load it in Fortran and use it like we've described. So that's what we call offline training. It became apparent in Laura Mansfield's paper that I think Jack mentioned earlier, that actually online, sort of online performance is important, because if you train your model based on this set of training data, if it then encounters something slightly different in the sort of real model run, then this can be difficult to, if it's out of sample, it's not going to perform well. But if you can adapt to that and learn from what's seen in the sort of deployment, then that can be beneficial. And that's what we would call online training, where you can continually update the model during model simulations where you're using machine learning. And then it's also relevant to, sorry, I should mention the connection here. So in order to do that, the online training, you need to be able to differentiate through your model. And that's with this automatic differentiation functionality. That's kind of used within PyTorch in this sort of propagation operator that you will have heard of. That is actually what updates the weights inside the model. But yeah, there's also this link to differentiable modeling more generally, which is quite a hot topic, I would say, in weather and climate right now, because people have these very large Fortran codes which aren't particularly amenable to differentiation very easily, and so they want to find ways that they can do it in order that they can sort of compute other things that they weren't able to compute before. So, for example, do sensitivity analysis, uncertainty quantification, and to estimate parameters. Hybrid models is a term that we've been using, which maybe is people haven't heard of before. We're just referring there to a model that uses both traditional methods and then also machine learning together. So why would we want to do any of this? If you can do this online training, it avoids saving large volumes of training data, essentially, which in some cases you might want to avoid if it's, for example, if it's data that has no other real purpose other than to train this particular case. It avoids the need for you to convert between Python and Fortran data formats, because when you create your training data, that's something you need to think about. It's not necessarily a hard problem, but it means you don't have to solve it. And also, it gives you the possibility to expand the scope of what your loss function is defined as. And I'll come on to that in the next slide, I think. And the main reason that people aren't doing much online training in Fortran is that it's quite hard to implement in most frameworks. And that's why we thought it would be something that would be very useful. When I said expanding loss function, what I mean is something like this. So typically your loss function is just a misfit against what's expected in the data. But in a web model or a climate model, sometimes there's a sort of downstream quantity that you're more interested in that isn't directly encoded within the model. So for example, if U here is the solution that you get from your physical model, and then UML is your output from your neural network or whatever it is you're using, then this is just a simple loss function that you could compute here, where it's an L2 error, for example. But you might have something more interesting where it's like a diagnostic quantity that you take the output of the model and then you do some other calculations on it, and then you want to compare those. And in order to make that work with online training, you need to be able to differentiate through all of that code. And so basically, this is the reason why we've been doing this work on automatic differentiation, is to enable people to do that. So that you can compute gradients of these things and therefore optimize the parameters. Implementing this had a few different steps. So we exposed this requires grad argument that you will have seen if you're familiar with PyTorch, and the backward method, which does this backpropagation. We also overloaded a load of operators, for example, for tensors, which allows you to do this kind of thing. And I provide a simple example here, which has actually got some outdated syntax, but it doesn't matter. This is actually not valid anymore. You can't pass an array directly like that, but it's a side note. You create a couple of tensors, A and B, and you give them this requires grad equals true. So basically what that means is that you intend to use these tensors in some computation that you want to differentiate. That's what that means. There's a step in between where we create some other scalars that don't need to be differentiated with respect to. And then we just compute some expression. So here it's just some arbitrary mathematical expression, doesn't really mean anything. But it just gives you a sense that you can just combine various different operations here and get an output tensor Q. And then once you've done that, you can call torch tensor backward Q. So what that will do is then actually drives the automatic differentiation and computes the derivatives. And you can then extract the derivatives dq by dA. So Q differentiated by the input A, and then also by B as well. And you get both of those at the same time, basically, because this is the reverse mode of AD, but that's another talk to go into the details of that. So that's automatic differentiation, and then optimizers and loss functions are things that we needed to expose in order to do online training. So we exposed a selection of different optimizers, so stochastic gradient descent, Adam, for example, you might have heard of. And even just with that, you can already do some quite cool stuff, because you can do like constrained optimization problems and sensitivity analysis kind of stuff. But if you want to actually do online training, then you need loss functions as well. And we've not actually got around to implementing any of the built-in loss functions. There's quite a lot of them in PyTorch. But we've got torch tensor sum and torch tensor mean, which are kind of good starting points for writing loss functions. And there's an example here that I won't go into the details of, but basically it shows that if you do this with PyTorch, which is in blue, or with FTorch in orange, you get exactly the same results. And it would be concerning if you didn't, because they're using the same thing under the hood. They're both using the same libtorch backend. But this is sort of a check that is indeed the case for an optimization problem. I'll mention a case study that's related to online training. So I've worked quite a bit on UKCA, which is the UK's chemistry and aerosols model, that's used by the Met Office. It's also used in UK ESM, which is the UK's Earth system model that contributes towards these CMIPs that we mentioned before. It has a whole load of different traces, I should say traces rather than trackers, between 85 and 200, which are different chemical species in the atmosphere, and between 300 and 700 interactions between those. So it accounts for a lot of chemistry that happens in the atmosphere. However, it's known to be a bit of a bottleneck for the Met Office's models. So it's about 25% of the runtime. is the unified model, which is their sort of current weather model. And then the chemistry solver, which is one of the three components inside UKCA, is 40% of UKCA's runtime. So there's a flame graph there, which shows in purple the sort of chemistry model. And previously in different projects, I did a whole lot of work on trying to reduce that, basically, trying to make it run faster. And ultimately, we came down to a problem that's related to how the solver is structured. Basically, there's this issue that the time step, adaptive time stepping is supported. So in different parts of the domain, you can use a different time step, which is not something you can do in many models, but because chemistry is sort of independent on each grid box, it's possible to do this. However, the time step that's required for the time stepping routine, it varies quite a bit. So in most cases, you can use quite a large time step of an hour, but in some cases, you have to use a very small time step because there's very advanced chemistry that's going on, more like complex chemistry that's going on, for example, over a megacity, or at certain points in the atmosphere, or when night becomes day, which is called Terminator, and which is quite interesting. So basically, it would be useful to know the time step in advance, is the sort of bottom line. And if we could know the time step in advance, it would allow us to avoid a lot of redundant calculation where you're trying to figure out what the time step should be. Like trying an hour, it doesn't work. Try half an hour, it doesn't work. Try a quarter of an hour, it doesn't work. And so this is kind of what we're doing in an ongoing project, which hopefully we'll have an intern working on this summer, which is using a machine learning model to predict, based on input data, what time step is required, and then doing this in an online training setting with FTorch. So it's got a nice sort of safe application of machine learning in a way, because if you replace your physics model with machine learning, then all sorts of things can happen. But if you just allow it to choose your time step, then either if it gets it wrong and it chooses too large a time step, then you'll just fall back on the original logic and just half the time step again. If it chooses one that's too small, then it's not necessarily the end of the world. It might just be unnecessarily small. So I will summarize FTorch. So it's all about using machine learning and numerical models, basically, in Fortran. It solves the problem of language interoperation for scientists that are working in Fortran and want to make use of machine learning and deep learning technologies. It's designed with both computational efficiency and also developer efficiency in mind, and it's helped to deliver science in climate research and beyond in lots of different examples that we've mentioned. It's built into the community Earth system model, which is really nice, and hopefully we'll be able to get it built into other models sometime soon. And there's been some recent developments on online training and automatic differentiation, which we'll give some more announcements about sometime soon. I'm going to pass it back to Jack, who's going to release.
Yeah, so as Joe sort of mentioned, this is ongoing work. We actually have some sort of allocation at the moment. to do this, the first half of which has been sort of cleaning up a lot of hanging issues, making sure that we are continuing to support this software sort of as something that is not on a project we're immediately deployed on, but things that need doing for the maintenance. The second bit of it is working towards sort of implementing some of these new features that people want. And it fortuitously happens that the first bit of the project was completed yesterday evening. So we thought it would be fun. What could ever possibly go wrong? There's no children or animals, just live demonstrations. But hopefully you are all invited to the release party of version 1.1. If we go ahead, there we go, 1.1. And so with that, I just say thank you all for coming. Thank you to people who've helped out with this work and given us funding and time to do it. And if you have any questions, please let us know.